Good afternoon, ladies and gentlemen. Welcome to your first online lecture video for Physics 1. Today we're going to be talking about Chapter 17, or Changes of Phase. Now before we get started with any of the actual content for this video, I want to apologize for a couple of things. First of all, this webcam that I'm recording this video on is probably older than most of us. It's like from the dark ages, and I'm sure you can tell from the video quality that's probably closer to a potato than a real webcam, but this is what we have to work with. I'll see what I can do about getting a better quality video to you in the near future. Also, you may have noticed there's this huge cardboard box in the background. I had a little bit of trouble getting the lighting just right in here to make a clear video. And I also want to apologize in case you see any cats in the video, like Lucky here. No, don't move the box. In any case, let us begin with Chapter 17 and Changes of Phase. Matter exists in 4 phases. These, of course, are solid, liquid, gas, and plasma. In the case of water, for example, the solid phase would be ice. Liquid would be water, and gas would be steam. Plasma is when everything gets completely ionized, generally because of all the energy, the kinetic energy in the substance, or the heat. Now the phase depends on the temperature, obviously, but also on the pressure that the substance is under. Matter can change between phases, but in order to do so, generally it either has to gain or lose energy, heat, for example, or sometimes if it undergoes a change in environmental conditions like pressure, it can also change phase. Now the book actually has 2 sections on going from liquid to gas, let's say. One on evaporation and one on boiling. And I'm pretty sure that most of us know that they're sort of one and the same. Obviously, the process where liquid goes to gas is generally called evaporation. And if you look at the liquid, generally the liquid by this point is boiling because it is vaporizing. Particles in a liquid all have different velocities, generally much lower ones than the velocities of particles in a gas made out of the same substance. That is to say, the water molecules in liquid water generally move slower than particles of steam, for example. When a liquid evaporates, it generally takes the kinetic energy of the hottest and most energetic particles with it. In that way, it keeps the liquid cooler. And that's why the author felt it necessary to have one section on evaporation and one on boiling. Water, for example, cannot go above 100 degrees C here at normal atmospheric pressure. When it gets there, it boils to keep cool. And I know that's a little bit of a cringy definition, but that's how the author chooses to word it. I would choose to say something along the lines of the really, really hot water particles, the steam particles, take a bunch of the heat or kinetic energy with it as the water vaporizes, and those particles leave the water and become steam. You remember when I said that pressure is also a factor in determining the phase of matter? Well, if you use a pressure cooker, like a crock pot or something like that, you make water boil at a higher temperature because the pressure is increased. You got that lid on it. It takes more heat to evaporate the water if the water pressure is already high, if there's already a bunch of steam inside the crock pot, for example. This is why a tea kettle boils once there is sufficient pressure equivalent to water right around boiling. The steam escapes the whistle spout, and you can hear that your tea is done even if you're in the other room. Also, if you've ever been camping somewhere up in the mountains at a higher elevation where there's less atmospheric pressure, it takes longer to cook something in boiling water. This is because there's less atmospheric pressure, so water boils at a lower temperature, and it takes longer to cook your food and to make it hot. Evaporating water also takes a lot of energy. It takes 1 gram of water about 2,200 joules of energy to evaporate. We call this the latent heat of vaporization. That means for 1 kilogram of water, it takes 2.26 million joules, or 2,260 kilojoules of energy. And that is the same as exploding 2 sticks of dynamite. That's why some doctors will use a mister or a misting device in order to cool someone down who has heat stroke. The ultrafine water particles evaporate very easily when they touch your skin because they spread out and don't require a lot of heat per unit volume to vaporize them. And that's why if you stand under a mister under a hot day, it's very refreshing and it keeps you cool. And that's also why some people walk around with a spray bottle, sometimes with a little fan on it on a hot day, because evaporative cooling works. The reverse of the evaporation process is called condensation. This is changing, of course, from gas to liquid instead. When a hot gaseous particle joins up with liquid particles, it brings heat with it. In this way, condensation is a warming process in the same way that boiling is a cooling process. But I think we all know that things only boil when they get hot, and things only condense as they're cooling off. When you take a hot shower, there generally isn't a lot of steam in the shower at the beginning, right? But after you've been in the shower for a few minutes, the steam starts to fog up the bathroom and it warms up some. When you're done with the shower, water isn't evaporating super fast as long as you stay in the shower when there's lots of steam. This is because the vapor pressure of the steam is high. There's a lot of steam in the shower and the bathroom. But if you step out of the shower, what happens? It's instantly very cold because the water on your skin evaporates more easily with less water vapor in the air. Condensation, because it's the reverse of evaporation, also takes 2,260 joules per gram for water. Just the same process in reverse. You're just absorbing the heat instead of releasing it. Freezing and melting, on the other hand, takes only 335 joules per gram, or almost a seventh, or a little less than a seventh as much. It takes about 6.7 times as much heat to vaporize water as it does to melt ice with the same mass. If we started with 1 kilogram of water at minus 50 degrees C and heated it up until it became steam at 150 degrees C, what would happen? Well, first you have super cooled ice. Ice that is cooled below the freezing point by another 50 degrees C. So the first thing that we have to do is warm the ice up to the melting point, and at that point it can melt. So, how much heat is required to do that? Well, if you remember from our lecture last week, Q is equal to mc delta T, so the heat required is equal to the mass of the ice that we're trying to melt, 1 kilogram, times the specific heat for ice, which is 2.06 joules, times the change in temperature, which in this case is 50 degrees. So it's going to take a certain amount of heat to warm the ice up. And then, once it gets to the melting point, 0 degrees C, we have to give heat to the ice to melt it. The latent heat of fusion, like I said before, is 335 joules per gram. Since we're talking about melting 1 kilogram of water, it's going to take 1,000 times that much, or 335 kilojoules, 335,000 joules. Lucky, please don't knock the box over. No, don't knock the box over, thank you. She's a good kitty. Where was I? Eventually, if we apply all 335 kilojoules of heat, no! Oh, you can see now why I wanted to have that box up there, because it's totally washing out the image now. And see if I can just get this where it was before. That's pretty good. It's blocking out most of the light now. Where was I? Now our next step, once all of the ice has been melted, obviously if we're going to get it to eventually being superheated steam, we have to heat the water up to the boiling point, right? We've got ice cold water now, ice that is just melted. We've got to heat it up until it can get to the boiling point, and then it can boil off. So Q equals mc delta T again. We got a mass of 1 kilogram. The specific heat for water, as we said in the last lecture, is 4.186 joules. And we're changing the temperature by 100 degrees C. That's the difference between 0 or freezing and 100 or boiling, right? So if we multiply those together, we're going to get a certain amount of heat required. If you want to follow along, as you should be, of course, like we do in class, just to make sure that I don't get any of the math wrong, if you take 1 kilogram times 4.186 joules per gram degree C times a temperature change of 100 degrees C, we should end up with 418.6 kilojoules, or 4.186 times 100 times 1,000, right? Now that's slightly more than the heat required to melt the ice, to melt 1 kilogram of ice, about 408 or 419 kilojoules. Now, we've finally got the ice up to the point, or what started out as supercooled ice, up to the point where it can boil, right? We first warmed it up to the melting point and then melted the ice and then heated up to the boiling point, and now that we've got 100 degrees C water, it can boil off. Now the heat of vaporization, as I mentioned earlier, is incredibly high, something like 2,250 joules per gram. And since we're melting 1 kilogram, we have to multiply that by 1,000, right? And so the total amount of heat required to vaporize 1 kilogram of water is 2.26 million joules. That was our 2 sticks of dynamite that I mentioned earlier. That's a lot. That's more than 5 times what is required to heat water from 0 degrees C to 100 degrees C. And that's why it may take water a while to boil, but it takes much, much longer if you want to actually boil all the water off until it's gone from the pot. That takes forever. Now, presumably, when we want to heat the water up now from 100 degrees C steam, since it's all boiled off, to 150 degrees C steam, we're going to do our Q equals mc delta T again. The mass, of course, 1 kilogram. The specific heat for steam is 2.03 joules per gram degrees C. And our change of temperature this time from 100 to 50 degrees C, or excuse me, from 100 to 150 degrees C is 50. So we got 1,000 times 2.03 times 50, and that's going to cost us about another 101.5 kilojoules. That's about a third of the heat required to change the temperature of water from 0 degrees C to 100 degrees C, and about, let's see, a 20th of the heat required to boil 1 kilogram of water, to make 1 kilogram of water go from 100 degrees C water to 100 degrees C steam. Long story short, if you look at the phase diagram that I've provided you, you can very clearly see that the branch, the horizontal branch that corresponds to the boiling or vaporization of water, is much, much longer than any of the other branches on this diagram, because it requires so much more heat to vaporize water than it does for any of these other phases or temperature changes or what have you. It takes a lot of heat to vaporize water. That may or may not be on the upcoming exam, so please take very careful note of the heat required during this process. Now sometimes different materials can go directly from solid to gas. We call that sublimation, right? And one of the very common substances that sublimate is dry ice or solid carbon dioxide. This is much colder generally than regular ice, and so sometimes we use dry ice to keep our ice cold, to keep our food cold for longer periods of time. This, of course, can only happen under certain temperature and pressure conditions. At atmospheric pressure, carbon dioxide boils at a very low temperature, and so we have to have special devices in order just to make this work. Thus it goes from solid straight to gas. And I've also provided you with a link for a video to showcase the sublimation of dry ice. It's also possible, at just the right combination of temperature and pressure, for all three stages of matter to exist at once. This is called the triple point. And if you have a temperature of 0.01 degrees C and a partial vapor pressure of 611.657 pascals, which is very, very low in comparison to atmospheric pressure, which is 101.3 kilopascals, or thousands of pascals. Now I've also provided you a link for the triple point so you can see what that actually looks like. If you look carefully and closely at the video, you'll see that there's bubbles coming out of the water, and that means that there's water vapor, but there's also very clearly liquid water and some ice. Thank you. I hope you've enjoyed this video. I will be providing you another video with the content for Chapter 18 shortly.